Hello, welcome to my channel. In this video, we are going to be taking a look at the recurrent relation of the Bessel's differential equation. So we'll start with the Bessel's function given in the form of g of n as a function of x given by this expression. So we got this expression from our previous video that dealt with the Bessel's differential equation. So we start from this function and we look at this function and notice that we can re-express this function as this expression where our 2 here and our x here have the same power, so we'll bring it up. So if we differentiate this expression, we have this. Why? Because our 2r minus plus n will come back. We subtract 1 from this to get this expression. And we also differentiate our x over 2 to give us half. Then we multiply, which is this. At this point, if we multiply both sides by x, we have x g prime of nx, then x over 2. So this x over 2 can go back into this part to take care of this 1 minus 1. Then also notice that this n plus 2r, we can split this equation into 2. So that n will be for the first one, 2r will be for the second one. So we have this expression. So n for the first part, 2r for the second part. Now, if you compare this expression with this g of nx, we notice that the only difference between this and this is just n. So n is a constant that can be brought out, and we are left with g of n. So we have x g prime of x equal to n g of nx plus 2r equal to this expression. Now we have 2r. What we can do from here is to split this expression again to x over 2, bring out x over 2 out and have n plus 2r minus 1, and see if we can cancel these 2 with the 2 at the bottom. Then the x here will come out. Then this r, we can take care of this r because r here can be written as r times r minus 1 factorial. So we have this expression. So this is what we have, and r minus 1 factorial. R can take care of this r, 2 can take care of this 2, leaving x below. So we have x, which is a constant, comes out. We are left with this. Now, if we compare this expression with that of gn of x, so we could recall that this particular one, because of this r minus 1, right, this summation can no longer start from r equal to 0. Because if it starts from r equal to 0, r equal to 0 here, we have minus 1 factorial, and minus 1 factorial becomes infinite. So hence, we make r start from 1. But we want to make this expression looks like that of the Bessel's differential equation. So what we do is to take this one back, so it becomes r minus 1 equal to 0. And that's how we have r minus 1 equal to 0. And we set it equal to s. So everything here, we set it to s. And we can make r the Soviet formula. So r equal to s plus 1. So wherever we see r, we replace with s plus 1. And this r minus 1 will be equal to s. So this expression reduces to this. So we have r minus 1 factorial equal to s factorial. R is x plus 1. R here will replace this expression. Then we finally have this. So we recall that our g of nx equal to this expression. So at this point, we notice that if we compare, we have s factorial, we have r factorial. We have n plus r, we have s plus n. So our s here can act as our r here can act as our s, but the difference between this and this is that we now have n plus 1. If we compare this and this, we have 2s, which is our 2r. We have n, which is n, but it is now having plus 1. So this expression here will be nothing but our gn plus 1 because of this extra 1. Now, but what we can note is that this expression, if we take the first term of this, the first term of this is positive. right? Because minus 1 raised by 0 is 1. But the first term of this is negative. So if we take the first term of this to be negative a, second term will be positive, third term will be negative, and as a result, if we factorize the minus out, we have minus a plus b plus c minus d plus this. So this expression will become negative x j of n plus 1 x. So that's how this one changes to minus, because the first term of this, when s is 0, will have minus 1 raised by 1, which is same thing as minus of this value. The second term is positive, third term is negative. So if we factorize our minus out, we have this. So that minus is what came about this minus here. We have our x, then this term is jn plus 1. So we can also resolve this particular expression, so the previous expression, which is giving us, we recall this expression, and we notice that the previous, the way we handled this one was to split this one into 2n plus 2r. But we can resolve it in another way by adding n and subtracting rn at the same time from this expression. And we have n plus 2r plus n minus n. I will take these two to become 2n plus 2r minus n. At this point, we can split this one into two parts, which is 2n plus 2r on one side minus n on the other side. So we have this expression, then the minus n parts. So we still see that this one is exactly equal to j of n. So this one, we can split this one into, we can split this one also into x over 2. We subtract 1 from this, n plus 2r, so that our 2 can take care of 2. Then we have n plus r here. Here becomes n plus r into bracket n plus r minus 1 factorial. So we have these parts. We've already taken care of this as n j of nx. We've already split this one. We can split this one now, which is giving us x over 2. The 2 takes care of these 2. X over 2, 2 takes care of these 2. We're left with x here. Then n plus r, we take care of this n plus r, and we have this expression. Now, if you compare this expression with that of j of n, you'll notice that what we have is n minus 1, n minus 1. So this expression will become j of n minus 1 times x. So we have this expression minus n j of nx. So at the end of the day, we have two expressions that we derived, which are, we now have this first one, which was derived earlier, and now this one. So we can see the connection between j of n is related to j of n and a term higher, which is n plus 1. We also have this expression, which is a term lower minus j of n. If we simplify this one by adding these two equations, we can get this expression. This same expression, if we subtract this one from this, we can get this one here. So these are the recurrent relation for the Bessel's function. And what we notice is that if we know our n to be, let's say, half, we can find minus j minus half and j 3 over 2. If we know our n, we can find the term higher or a term lower. That's how these Bessel's functions are related. Hopefully in my next video, we'll see how these particular Bessel's recurrent relations are used. Hope you enjoyed this video. Thank you for watching.